Okay, good afternoon, guys. So before we get started on the content of today's lecture, I want to do a little bit of housekeeping stuff. So a few things. We have the assignment and we have the test. So for assignment 1, do keep in mind that it's due on Friday, which is tomorrow. You may have noticed that 3115, which is the room you have to submit it to in the drop boxes, you may have noticed that that lab closes at 4:30. The hours of that lab changed after I made up the assignment, unfortunately. So out of fairness to you, I will stay in the lab from 4:30 when it closes until 5, so you do have until 5 to submit. But for subsequent assignments, they'll be due at 4 p.m. instead of 5 p.m. So you don't have to do this every time. So I suggest you start assignment 2 an hour earlier than you would have otherwise. All right. So that's for the assignments. For the tests, your first test is next week. This is how it's going to work. You're going to go to your tutorials. You'll have 45 minutes to write the test. It's 2 pages. It's double-sided, so 1 sheet, front and back. I don't remember how many questions. You have 45 minutes to write it. It's worth a lot, so study really hard for that. There are 4 tutorial sections in this class, and they are on Monday, Wednesday, and Friday, which means that the Friday people would seem to have a distinct advantage and that they can talk to other people who have already written the tests. To counteract that advantage, I'm going to post a sample test tonight, immediately after the lecture when I post the notes. Most people don't believe me when I say that the sample test is the same as the test. It's basically the same as the test. Slightly different questions, but all the same kind of questions. So obviously you're at some point going to have to know something about translating a sentence. So it'll be a slightly different sentence, right? Maybe instead of being about discrete math, it'll be about calculus. But the subject doesn't change how you do these. So tonight, look at the sample test. If you go through the sample test and you find yourself unable to do it, I promise that you will fail the test next week. I guarantee it. You need to be able to do the sample test in order to do well on the test next week. Okay, now maybe you don't believe me that I would give so much away on the sample test. In test 2, you will believe me. Do the sample test. I can't stress that enough. It's really, really important that you do that. Any questions about how the tests are going to work? Okay, so that's what you can look forward to next week. Don't skip the tutorial next week. So last time we were talking about arguments, and specifically we were talking at the end of class about arguments that had quantifiers in them. And we talked about universal instantiation and generalization and existential instantiation and generalization. And all of the arguments I showed you worked out using these rules. But these rules have certain requirements, 2 of them in particular. So I want to do one quick example. Whoops, shouldn't be in red. I want to do one quick example where things fall apart, just so you know not everything works. All right, so here's my argument. If John knows discrete math, he will pass this course. John knows discrete math, which I do. Therefore, everyone will pass this course. All right, we can see that this is not a valid argument, right? That clearly doesn't make any sense. We don't need to appeal to logic or anything like that. It's clear on the face of it that it's not valid. But let's go through the motions and see what happens when we start applying these rules and see what in our rules causes us not to be able to infer that conclusion. So if we let dx be x knows discrete math, and px denote x will pass this course. Then what do we have? Well, we have we have D John implies P John. That's premise 1. Premise 2 is D John. And the conclusion is for all x, px. Okay, and the universe of discourse is the set of all people, say. All right, so we can see that this is probably not going to be valid. But where do things break down? So let's pretend I wasn't too careful and I started applying these rules. So I have that D John implies P John. So I am allowed to conclude P John. And that's by modus ponens of 1 and 2. Does anyone have a problem with that? We've been doing that for the last class. Where things start to break down is you say, okay, well, I have P John and I want for all x P something, Px. So what you might be tempted to do is say, okay, well then I can infer for all x Px, and that's by universal generalization of 3. Why am I not allowed to do that? Yeah?
Because you know something about like that John knows.
Yeah, so I already know something about the variable in 3. And in fact, it's not a variable, it's a specific thing. It's John. Right? So I know something about this. I know something about John, and that is that it's not arbitrary. And it's not arbitrary, and therefore I can't do universal generalization. It's wrong to do that. All right, now in this case, it's pretty obvious, right? And in fact, once you're good at it, it's obvious all the time that it happens. But this is what you're not allowed to do. So this is what I mean when I say you can only apply universal generalization when it's an arbitrary element. It's something you don't know anything about. And John is certainly not an arbitrary element. It's a fixed element that you picked. Okay? Is that distinction clear? Yeah.
So if it was P of X, then we would be able to use universal generalization.
Right, so the question is, if it was P of X, would I be able to do this? And the answer is yes, as long as that X was, derived from something else. That might have come from a universal quantifier or something like that. In that case, yes, it would be okay. Other questions? All right, so that's the last example I wanted to do for arguments. What we'll do now is move on to the next topic in this course, and that's proofs. This is what we'll be doing for the rest of the course in different contexts. Okay? So a proof is really just an argument. So all of the examples we saw about arguments, I gave you the argument and I asked you, is it valid or is it invalid? What we're going to do now is find ways to come up with arguments that are valid. Question?
Are proofs going to be on the test?
Yes. Proofs will be on the test. So that's a good point. The test covers up to the end of this lecture. So everything I talk about today is fair game for the test, to be clear. Other questions? Yeah?
So that example above was invalid?
Yes, this is invalid. But I didn't say why it's invalid. So the way you see that it is invalid is you give true settings to all of these things. So you would say D John is true, P John is true, and PX is false for Mike, whoever Mike is. Mike's a person. That shows that this is false. Right? I gave true settings that made the premises true, but the conclusion false, and therefore it's invalid. All right, so moving on to proofs. How do we go about forming arguments that are valid? That's really the question we're asking ourselves when we do proofs. So there's a couple of different techniques, and I'll talk about the techniques today. The first technique is to do what's called a direct proof. So let's say you're trying to prove an implication. So the conclusion that you want to infer is an implication. So to prove P implies Q, if I want to prove that that implication is true, one thing I can do is start by assuming that P is true. And then prove that Q is true under that assumption. Okay? And that makes sense because if the thing on the left is true, then the thing on the right is true, that implication becomes true. And that's what we wanted to show. So let's do an example. I want to prove that if n is an odd integer, then n squared is an odd integer. So this is the kind of question you might get asked on a test. Notice that it's an implication because it's if, then. That's how I know it's an implication. The thing on the left of the implication is this, and the thing on the right of the implication is this. So what I do is I assume the thing on the left. Okay, so I assume that n is an odd integer. That's the assumption that I make. And now I think to myself, what does that mean? So what is an odd integer? What do they look like? Yeah?
An integer that gives you a remainder of 1.
When you divide it by 2. So it's an integer that gives you a remainder of 1 when you divide it by 2. One way to write that is to say that if it's an odd integer, then it looks like 2 times a number plus 1. Right? Because when you divide 2 times k plus 1 by 2, you get a remainder of 1. Right? You get k remainder 1. Okay. And that's for some integer k. So I know that k is some integer. All right? This is a very common trick. When you're given that something is an odd integer, you should know that you should probably write it as 2 times an integer plus 1. If it were an even integer, it would just be 2 times an integer. That's a common trick that you have to know for, say, next week. All right. So, if I know that that's true, I know a lot about n now. I know the form that n has, and I'm shooting to figure something out about n squared. So let's try squaring n. N squared, well, n is just 2k plus 1. So now I need to do a little bit of math and figure out what that is. What is 2k plus 1 all squared? Yeah. 4k squared plus 4k plus 1. Okay, so that's something you need to be able to do. This is basic math. You need to know how to do that. If you can't do it all in one step, write 2k plus 1 times 2k plus 1, and then do first, outer, inner, last. All right, so now that we have this, we know what n squared looks like, and we want to try to convince ourselves that that is odd. Okay, well, remember odd numbers have the form 2 times an integer plus 1. So if I factor out a 2 from the first 2 terms, I'm left with 2k squared plus 2k, and then I still have that 1 hanging around. And if k is an integer, then 2k squared plus 2k is also an integer. So this says that n squared has the form 2 times an integer plus 1. So what does that mean? It means it's odd. So therefore, n squared is an odd integer. And notice what happened was I assumed that n is an odd integer, and under that assumption, I derived the fact that n squared is an odd integer. Okay, so these match up, and these match up. That's all a direct proof is. A direct proof is you want to prove that an implication is true, so you start on the thing with the thing on the left, assume it's true, and using that assumption, you prove that the thing on the right is true. That proves that the implication is true. Right? Because the only way it can be false is if you have true implies false, but you don't have that. The thing on the right is true. Is this clear? Any questions about this technique? Question, yeah.
It's hard to prove that with assuming n is true to see the contraposition.
Yeah, and that's exactly what the next kind of proof will do. That's called an indirect proof. So the idea is if you have difficulty proving this, so you assume that n is odd, and then for whatever reason you have trouble proving that the thing on the right is true, one thing you can do is take the contrapositive of the implication and prove that that's true. That's a great technique. Yeah. Other questions? All right, so let's talk about that. That's called an indirect proof. So recall that P implies Q is exactly the same as not Q implies not P. Right? So therefore, to prove P implies Q, you could instead prove not Q implies not P. And if you do that directly, you would end up proving you would assume not Q, and under that assumption, show that not P must be true. And when you do a direct proof on the contrapositive, that's called an indirect proof. So these are very similar techniques. So let's see an example of that. So prove that if 3n plus 2 is odd, then n is odd. That's what we want to do. Now you could try to prove this directly. Try that at home and see where you get. I'm going to prove this indirectly. The way you generally want to do proofs is try to do it directly first, and if you get stuck, do it indirectly. The thing that tells me in this example that I want to do it indirectly is I look at both sides. I have an n is odd on this side, and I have a 3n plus 2 is odd on that side. I like to assume the simplest fact. Right? And the simplest fact here is that n is odd, because 3n plus 2 is a more complex fact. Although I agree that that distinction is at least a little bit arbitrary. But nevertheless, it's a good tip. It's a good starting point. All right, so instead, I will prove the contrapositive of that, and that is if n is even, then 3n plus 2 is even. Right? That's the contrapositive of the original implication. And now I'll just do a direct proof of that. So I will assume that n is even. Well, if that's the case, then n must be equal to 2 times k for some integer k. And I want to know about 3n plus 2. So 3n plus 2 is equal to 3 times 2k plus 2 is equal to 6k plus 2. And now I'm shooting for the fact that 3n plus 2 is even. So at some point I'm going to have to factor out a 2. So if I factor out a 2, what's left is 3k plus 1. Now if k is an integer, then 3k plus 1 is an integer. So this is 2 times an integer, which means it's even. So under the assumption that n is even, I derived that 3n plus 2 is even. And so the contrapositive of that, if 3n plus 2 is odd, then n is odd. Well, that must also be true, because the implication is logically equivalent to its contrapositive. Any questions about this proof? Yeah? Yeah, so if you wanted to do a direct proof here, what you would say is 3n plus 2 equals 2k plus 1, and then somehow solve for n. That's what you would want to do. So let's see what happens when you do that. 3n plus 2 equals 2k plus 1, and now I'd like to solve for n. Okay, so 3n is equal to 2k plus 1 minus 2. And then that's the same as 2k minus 1. And n is equal to 2k minus 1 over 3. Does that give me anything? Does that tell me if n is even or odd? Is it even clear that n is an integer at that point? No, it's not. Right? So if 3 doesn't divide 2k minus 1, then you're in trouble. So that's why an indirect proof is better here, because we try to direct proof and we get stuck. And we'll see some other examples of that later on. That's why you go to an indirect proof sometimes. All right, let's do another example of an indirect proof. And this is a case where you do in fact get stuck. I want to prove that the sum of two rational numbers is rational. What's a rational number? Yeah?
Any number that doesn't have a square root negative 1.
Not quite. Yeah?
N over D or N and D are
Almost. One exception.
almost not zero.
Yeah, exactly. So a rational number is the ratio of two integers where the bottom integer is not 0. All right, so let's write that down. It's A over B, where A and B are integers, and B is not 0. That's what a rational number is. That's another important thing to know for, say, next week. So this course isn't about even and odd numbers. It isn't about rational numbers, but we need to know about them to do some at least mildly interesting proofs. All right, so let's try to prove this directly. If we want to prove this directly, we start with, the first thing we do is we rephrase this. So the sum of two rational numbers is rational. What is that saying as an implication? Or is that even an implication? Yeah?
If A and B are rational, then A plus B is correct.
Yeah, you can rephrase this as if A and B are rationals, or just rational, then A plus B is rational. That's one way to do it. All right, so that's good. Now we've got it phrased as an implication, which is what we're familiar with. So let's do this. We're going to assume this, A and B are rational. So since A is rational, A is equal to, I don't know, P over Q, where P and Q are integers, and Q is not 0. Similarly, since B is rational, B is equal to R over S, where R and S are integers, and S is not 0. A very common mistake here would be to say A equals P over Q and B equals P over Q. They both have that form, but that statement would only be true if A happened to equal B, right? So that would then be proving if A is a rational number, then 2A is a rational number, which is fine, that is also true, but that's not the statement we're trying to prove. The same kind of thing would happen if I said you have two even numbers. Well, you couldn't say they're both equal to 2k. One would be equal to 2k1, one would be equal to 2k2, or something like that, or use other letters or whatever you like. All right, so now we know something about A over B. So now we want to know about A plus B. A plus B is what? Well, it's P over Q plus R over S. And what is that sum? Who remembers how to add fractions? Yeah. PS plus RQ over QS. Exactly. You multiply this one by Q on the top and bottom, and you multiply this one by S on the top and bottom, and that's exactly what you get. So now we want to decide, is this thing a rational number? So we ask ourselves, is it an integer on top? The top is PS plus RQ is an integer. Well, if you have an integer times an integer, you get an integer. And if you add two integers together, you get another integer. And similarly, QS is an integer. That's easy to see. And there's one other thing I have to check. Yeah? Well, I just need to check that QS does not equal 0. And QS is not equal to 0 because neither of Q and S are 0, as you said. The only way a product can be 0 is if one of the things you're multiplying is 0. Right? There's no other way a 0 can come out. And I know that Q and S aren't 0 because I stated that up here. Right? That's why it's always a good idea to write down exactly what you're given. So this shows that A plus B is rational. And this is hardly groundbreaking, right? If you add two rational numbers together, you get a rational number. That makes sense. Any questions about this? All right, so let's move on to another example. The only way to get good at proofs is to do lots of examples. Let's say prove that if n is an integer and n squared is odd, then n is odd. All right, so let's say for whatever reason, I wanted to try direct proof first, even though that's sort of contrary to the advice I already gave you. So if we wanted to do a direct proof, well, we would assume n is an integer and n squared is odd. And then we would say, well, since n squared is odd, n squared is equal to 2k plus 1 for some integer k. And now notice that we want to know about n. Right? We want to know about n. So n is just the square root of n squared. Right? And that is equal to what? Well, it's equal to the square root of 2k plus 1. What do I do with that? Yeah? Yeah. So if n is negative, then, I mean, we still have the notions of odd and even defined. That's not an issue.
Yeah, but n squared
N squared will still be non-negative, right? Because when you square a number, it becomes non-negative. Other thoughts? Is there anything I can do with the square root? Not that I can see. So at this point, you would say, I'm kind of stuck. We want to know something about n, and it's not even clear that the square root of 2k plus 1 is an integer. All right, so when you get stuck doing a direct proof, you should try backing up and doing an indirect proof. All right, so this would be saying assume that n is even, right? Because now I'm going in the other direction. It's the contrapositive. So I negate the right side and assume that. Assume that n is even, and now I want to show that n squared is even. So always have a good idea of what you're trying to show somewhere. I want to assume that n is even and show that n squared is even. Well, since n is even, n equals 2k for some integer k. Great. So that means n squared is equal to 2k squared, which is equal to 4k squared, which is equal to 2 times 2k squared. One very common mistake here would be to say, instead of 2k squared, to say 2k squared. If you do that, you'll still get the right answer, but your math is wrong. Yep?
But if we're taking the contrapositive, then don't we have to say that n is not an integer?
If you're taking the contrapositive of this statement. So the negation of this statement would be n is not an integer, or n squared is even. So if we show that n squared is even, then it's still true. It doesn't matter whether or not n is an integer.
All right.
Yeah. Other questions? All right. So now we're done, because if k is an integer, then 2k squared is an integer, and that means this is 2 times an integer, which means it's even. Any questions about that? All right, so the next kind of proof you'll see is called a vacuous or trivial proof. And I really only include this for completion and for thoroughness sake, for the sake of thoroughness, because I won't ask you any questions like this because it's silly. All right, so when you're trying to prove P implies Q, and it turns out that P is false, then you don't have to do anything, right? Because false implies anything is true, so you're done. So when trying to prove that P implies Q and P is false, the statement follows automatically. You don't have to do anything. All right? So if I wanted to say, do something silly like this, let's let Pn denote the statement, if n is bigger than 1, then n squared is bigger than n. And I wanted to prove that P0 is true. So P0 says if n is bigger than 0, if 0 is bigger than 1, then 0 squared is bigger than 0. So is that statement true? Yes. Right, it's true, but who cares? So this thing here is false. This thing here is false, but it doesn't matter. And this is false implies false, which is true. So yes, the implication is true. That's an example of a vacuous proof, because the implication you're trying to prove is true. The thing on the left is false. So it's trivial because you don't have to do anything. The thing on the left is false. I won't give you examples like that because I don't like asking questions where the trick is that you don't do anything. All right. What's more interesting and is commonly used, and will certainly come in handy next week, is the proof by contradiction. Or maybe it won't come in handy. I don't remember. All right. So suppose you want to prove, let's get away from proving implications for the time being. I'll show how this sort of links up with that later. Let's say that I just wanted to prove the proposition P is true. Okay, I just want to prove that P is true. One way I can do that is by showing that if I assume the negation of P, then I'm in big trouble. Something weird happens. There's some contradiction, like 1 equals 0. If I want to show that P is true, I say, okay, well, assume that not P is true. And if I can derive that under that assumption 1 equals 0, well, then something's gone wrong, right? That can't be the case. And the only way that I could have arrived at that false conclusion is if my initial assumption was incorrect. And my assumption was that it's not the case that P. So the only alternative is P is true. So we can formalize that if that sounds weird. So suppose we want to prove P. If we can instead show that not P implies false, so really what this means is not P leads to a contradiction, then P, well, so then not P must be false. And so P must be true. And this makes sense because I've proved that this thing here, not P implies false, I've proved that that's true somehow. So somehow I've proved that that's true. What's the only way that that thing can be true? Right, the only way I can do that is if not P is false. Because if it were true, then I wouldn't have been able to prove that it's true. Right? I would have come out as false because true implies false is false. But I got the answer true. So not P has to be false, which means that P has to be true, because those are the only two alternatives. Right? It's either true or false. So that's what a proof by contradiction is. Okay? Now, that's true for when you're talking about a single proposition. This same thing works with implications just fine. So if you wanted to prove P implies Q by contradiction, then what you want to assume is that it is not the case that P implies Q. Right? You assume the negation of the thing you're trying to prove. And the negation of this is just the negation of not P or Q, which is the same as P and not Q. So if you want to prove an implication by contradiction, you assume that the left thing is true, but the right thing isn't. And if you can prove that that leads to some kind of contradiction, well then the negation has to be false, which means the original implication is true. Right? If this seems weird, let's do a few examples, and then hopefully it'll clear things up. So here's the first example. I want to prove that root 2 is irrational. Notice that this doesn't really have an implication kind of feel to it. So that's one thing that tells us that we want to do a proof by contradiction. The other thing that tells us we want to do a proof by contradiction is the fact that we're being asked about something being irrational. And we haven't talked about being irrational yet. We don't know what that means, but we do know what it means to be rational. So that's why you might want to try negating something so it becomes something you do know about. All right, so let's try a proof by contradiction. So we'll instead assume that root 2 is rational. And now we're going to do a bunch of steps to try to arrive at some kind of contradiction. Something like 1 equals 0. And if we can do that, and we know that all of the steps we made were valid, then the only conclusion we can draw from that is the assumption we made must be wrong. That's the only thing that could have gone wrong. All right, so if root 2 is rational, then root 2 is equal to, let's say, a over b, where a and b are integers, and b is not 0. So basically it's a fraction that has an integer numerator and denominator. Is there anything else I can assume about a rational number? So what about a rational number like 2 over 4? Is that a rational number? Yeah. Is there another way I can write it? 1 over 2. And what do I like about 1 over 2? It's in lowest terms. So I can assume that a and b are already in lowest terms. So I'll just say, and a and b are in lowest terms. Is that fair? Right? It's rational, so it's some fraction, and I'm saying this is the fraction in lowest terms. If there's only one fraction, then it's that one. But if there's more than one fraction, it's the one in lowest terms. Does everyone agree that I'm allowed to do that? Does anyone think I'm not allowed to do that? Okay, so I'm allowed to do that by popular opinion. So now let's start working on this thing. So I don't like square roots. Square roots are gross, they're hard to reason about, so the first thing we should do is get rid of square roots. So since root 2 is a over b, we could also just square both sides and say 2 is equal to a squared over b squared. That's okay. I don't really like fractions either. They're kind of hard to reason about. So I'm going to multiply both sides by b squared to get 2b squared is equal to a squared. Is that okay? So this says that a squared is even. Right? b is an integer, so b squared has to be an integer. So 2b squared is 2 times an integer, and since that's a squared, that means a squared is even. If a squared is even, what do I know about a? A is also going to be even. Does everyone believe that? Okay, so if you don't believe that, do another little proof. Do a proof that says, if n squared is even, then n is even. Prove that's true on your own, and at that point you can use that fact. I'm not going to do that here, but it's very similar to the other examples we did. All right, so we did, what did we do up here? So it's basically exactly like this one except in reverse. So this one here applied to even integers, everything goes through just fine. All right, great. So now we know that a is even. So let's say let a equals 2c for some integer c. All right, so that means that 2b squared is equal to 2c squared, right? Because a is equal to 2c. All right, so that means that 2b squared is equal to 4c squared. Still good? Just expanding out the brackets. All right. So now I'll say b squared is equal to 2c squared. Right? I'll divide both sides by 2. So what does this mean about b squared? Right, it means that b squared is even. And if b squared is even, then b is even. Exact same logic as in the previous one. All right, so now I know that a and b are even. And that is a problem or no? Is it okay that a and b are both even? No. So why is it not okay that they're both even? Yep.
Because we already assumed that A and B are in lowest terms, and if they're not in lowest terms, then we can divide. Then we should be able to divide both of them by 2.
Right. A and B are supposed to be in lowest terms, but they're both even, which means I could divide both by 2 to get a smaller fraction. So that's a contradiction, right? I derived that they were in lowest terms, but now I've shown that in fact they're not in lowest terms. So that's like saying P and not P. They're in lowest terms and they're not in lowest terms. That's a contradiction. All right, so to highlight that, I have A and B are in lowest terms. They are not in lowest terms. This is a contradiction. And the only thing that possibly could have gone wrong is assuming that root 2 is rational. Because everything else I did was completely valid inference. It was completely good logic. The only thing that I wasn't sure about was root 2 being rational. Everything else followed perfectly. So my assumption must be wrong. So the square root of 2 is irrational. It cannot be written as the ratio of 2 integers. You can't do it. That's an important fact that you should know for next week. If you are ever in a situation where you need to know a number that's irrational, you should think to yourself, oh, root 2 is an irrational number. That's an important fact to have in your bag of facts. All right, so any questions about how I did this proof? Yeah?
Just a general question. Is this, like, would root 2 is irrational be something we can use as a starting point for another proof?
Right, so the question is, can you use this fact in your own proofs? Yes, anything I prove in class is fair game for you to use as part of your proof. So if at some point on a test or an assignment you needed to know an irrational number, you could just say root 2 is irrational without proving it. That's completely fine. The only exception is if on a test I asked you to actually prove that root 2 is irrational, then you can't just say, oh, you proved that in class. That being said, I wouldn't do that because I don't need you guys to memorize these things. I just need you to understand the concepts. All right, so the next technique that we're going to talk about is called the proof by cases. All right, so the proof by cases says, what if you want to prove a disjunction that implies something? So we want to prove a statement of the form P1 or P2 or and so on. Let's say up to Pn implies Q. Okay, let's say we want to prove a statement of that form. That's difficult to do using a direct proof because you have to assume that a disjunction is true. And it's kind of a weird thing to assume that a disjunction is true because all that means is at least one of them is true, and that's hard to reason about. So instead what you do is you apply implication equivalence and De Morgan's law and then implication equivalence in the other direction to get this. Instead you prove P1 implies Q and P2 implies Q and P3 implies Q and so on all the way up to Pn implies Q. That's what you do. And this is much better because although you have to prove more implications, within each part of the proof, you know something for sure. Right? I'm telling you for sure that P1 is true, and then derive that Q is true. Instead of one of P1, P2, P3, all the way up to Pn is true. That's not as informative. Right? We always like our proofs to have very specific facts in them. That gives us more to work with. So let's see an example of proof by cases. Okay, I want to prove that if x and y are real numbers, then the absolute value of x times the absolute value of y is equal to the absolute value of x times y. So the product of absolute values is equal to the absolute value of the product. Okay, so what's the trick to this one? What makes this kind of hard? So if there weren't absolute value bars, this would be very easy. The thing that makes it hard is the absolute value bars. What do absolute value bars make you think of? I guess there's no wrong answer, but negative numbers is what I was looking for. So the cases you have to consider depend on the behavior of the absolute value function. And the behavior of the absolute value function depends on whether the things are positive or negative. So we're going to have 4 cases because x can be positive or negative and y can be positive or negative. Right? So you have 2 times 2 is 4 cases to consider. So case 1 will be that x is bigger than or equal to 0 and y is bigger than or equal to 0. All right. So in that case, the absolute value of x times y is exactly the same as the absolute value of x times the absolute value of y, because they're both non-negative. And that's exactly the same as the absolute value of x times the absolute value of y. This is the easy case. They're both positive, so the absolute value function does nothing. Next case is a little bit more difficult. X is bigger than or equal to 0. Y is less than 0, strictly less than 0. So y is now a negative number. So the absolute value of y is equal to minus y, and that's bigger than 0. Right? Because y is negative, so minus y is positive. So far so good? All right. So if that's the case, then x times y is equal to x times minus y. Right? Because y is negative, so minus y is positive. Since x is non-negative, it's equal to its absolute value. And minus y, I just set up here, is equal to the absolute value of y. So we get that. So this shows that the absolute value of x times y is the absolute value of x times the absolute value of y. Is that okay? All right, case 3 is basically the same, except x and y are switched. In this case, x, the absolute value of x, is minus x, and that's bigger than 0. And we know that x times y is equal to minus x times y, which is the absolute value of x times the absolute value of y. And then the very last case that I have to consider is case 4. And that's when they're both negative. And in that case, the absolute value of x is minus x, which is bigger than 0, and the absolute value of y is minus y, which is bigger than 0, bigger than or equal to 0, I should say. And actually, that's true for all those as well. And now, the absolute value of x times y is minus x times minus y, which is just the absolute value of x times the absolute value of y. Yeah? So x is less than 0, so the negation of that is minus x is greater than or equal to 0. So that's why I have that there. Other questions? Yeah? Right, so in this, if we look up here at the technique, all of the cases have to be true because I have ands between each one of them. So every single case has to hold. And what you need to notice is that these 4 cases cover all possibilities. Right? There's no weird fifth thing that can happen because x is either positive, or I should say negative or non-negative, and y is either negative or non-negative. Right, because 0 is neither positive nor negative. Any other questions about this proof? All right, so let's move on to another technique. The next technique will be equivalence proofs. And this will be important for next week. So, to prove a biconditional, P if and only if Q, you do 2 proofs. You prove P implies Q and Q implies P. And you can do those however you like. You could do them directly or indirectly, by contradiction, whatever works. So when you're proving a biconditional, you're really doing 2 proofs. Right? If you prove that if you want to prove P if and only if Q, first you prove if P then Q, then you prove if Q then P. So whenever I ask you to do a proof that has an if and only if in it, I'm really asking you to do 2 proofs. And if you just do one of them, you're forfeiting half of the marks for that question. Okay, that's very important to understand. So you need to really look for the phrase if and only if. If and only if, and sometimes that's abbreviated if with 2 F's. It's really important to notice that, because if you don't notice that, you're giving up half the marks for that question, and that's not a good idea. So a common error is to miss one of those. All right, so let's see an example of that. I'm going to prove that n is odd if and only if n squared is odd. Okay, and notice that I have an if and only if here. That's really important to pick up on. You have to carefully read the question. So we have to prove two things. First, we have to prove if n is odd, then n squared is odd. And after we're finished that, we have to prove if n squared is odd, then n is odd. It goes in both directions. That's critical. So we must prove two things. If n is odd, then n squared is odd. And if n squared is odd, then n is odd. We have to do both of those things. All right, so we'll do the first one directly. So this one up here I'll call number 1. That's number 2. Number 1 we can prove directly. Assume n is odd. Then n equals 2k plus 1 for some integer k. So n squared is equal to 2k plus 1 squared, which is 4k squared plus 4k plus 1, which is equal to 2 times 2k squared plus 2k plus 1. And I did that really quickly because we already did this, right? We did it as a single proof. Now we're doing it as part of a proof of a biconditional. All right, so this thing here is an integer. So this thing here is an odd integer. So that's the first step of the proof. That works. That's the first direction. Now we need to do the second direction. It turns out that this direction is easier if you do an indirect proof. Why would I want to do an indirect proof here? Other than the fact that we already saw this and see that it doesn't work. Any thoughts? Yeah? Yeah? Yeah, you want to assume the simplest fact. So that's not necessarily the least amount of information. It's the information that's most easily stated. N is simpler than n squared. Okay, that's sort of a non-precise notion. The reason I want to do that is because I know the form of the thing that I'm assuming. And if I have other operations in it, it's harder to solve for the thing I'm looking for. Right? If I know n squared, it's harder to solve for n because I have to take a square root. If I know n, then it's easy to solve for n squared because all I have to do is square both sides. Squaring is way easier than taking the square root. And if you don't believe me, try doing a few of these and you'll see. All right, so assume that n is even. Then n equals 2k for some integer k. You might think it's weird to reuse k. I consider both parts of these proofs to be sort of independent, so it's okay to reuse things as long as it's clear that that's what you mean. All right, and at that point, n squared is equal to 2k squared, which is equal to 4k squared, which is just 2 times 2k squared. And 2k squared is an integer, and so 2 times an integer is an even integer. And that means that part is true. So we proved both directions, which means the biconditional is true. Does that make sense? All right, so let's move on. The next type of proof that you'll see is called an existence proof. All right, and for an existence proof, you just want to prove that something exists. Yeah? Right, so the question is, when can you stop in these proofs? It's not enough just to stop here. you need to say something about it having the form of an odd integer or the form of an even integer. You don't have to say it exactly like I've done here, but you can't just say, oh, it equals 2 times 2k squared plus 2k plus 1. You need to say something after that. All right, so existence proofs. So to prove that something exists, what you need to do is prove that there exists an x such that px, where p is whatever property you're trying to seek to prove. There's two types of ways to do that. There's the constructive way. The first is the constructive way. And that is where you give an A such that PA is true. Right? So if I ask you to prove that something exists, one way you can do that is to say, there it is. That'll do the job. The other way is to prove it some other way. It's kind of mysterious. It's non-constructive. So some other way. And there's no hard and fast rule, but at the end of it, you've convinced me that it exists, but I don't know what it is. And that seems really weird to non-mathematicians, but it happens all the time. I'll do an example in a second. Yeah? You'll have to decide on your own. So if I gave you an implication, for example, it would be up to you to decide whether you should prove it directly or indirectly, or with proof by contradiction or by cases or whatever. All right. So I'll do an example of each. One is prove that there exists an integer that can be written as the sum of cubes in two different ways. So I want you to prove that such a number exists. Any guesses? This isn't really fair, but any guesses? 1,729. It's equal to 10 cubed plus 9 cubed, and it's also equal to 12 cubed plus 1 cubed. So that's a proof, right? I gave you the thing you were looking for, and I showed you that it satisfies those two things. So it's not enough just to say 1,729. That's not a proof, that's a guess. You also have to show that it satisfies the property you want it to. And I did it here by showing you it's 10 cubed plus 9 cubed, and it's also 12 cubed plus 1 cubed. Okay? And I'm pretty sure that's the smallest number that has that property. Okay? It's constructive because I know what the number is, and it's a proof because I showed you that it satisfies those properties. Here's another example of a non-constructive proof, which a lot of people think is kind of a really strange thing, and I guess it is. So prove that there are two irrational numbers, x and y, such that x to the y is rational. So I want to prove that there exist two irrational numbers such that when I compute x to the y, I get a rational number. Okay, so I'm going to do a non-constructive existence proof. So this is asking about some irrational numbers, and the only irrational number I know right now is the square root of 2. So root 2 is an irrational number. Right? We proved that. So I want to look at x equals y equals root 2. So in that case, I have root 2 to the power root 2. Is that rational or irrational? It's not clear, right? I mean, it is either rational or irrational. It has some concrete answer. But I don't know just by looking at it. So what are the possibilities? Well, it could be rational, or it could be irrational. So let's say it's rational. So if it's rational, then I'm done. Right? Because if it's rational, then x equals y equals root 2, and x to the y is rational, and we're done. Does everyone agree? Okay. So the only other thing that can happen is it's irrational. Right? So if it's irrational, then I know that root 2 is irrational, and root 2 to the root 2 is irrational. Now I know that there's two irrational numbers. So what I'll do is I'll take x as root 2 to the root 2, and y as root 2. And if I do that, then x to the y is root 2 to the root 2 to the root 2. What is that? So I get root 2 in the bottom, and then in the top, I get root 2 times root 2, which is just 2. So this is root 2 squared, and that is exactly the same as 2. And 2, of course, is just 2 over 1. So, therefore, the claim is true. So in either case, I found x and y such that x and y are irrational and x to the y is rational. I don't know what case is true, but I do know that exactly one of them is true. So this is non-constructive because you don't know what x and y are. You know that there's a few choices for x and y, but you don't know which one is correct. Okay, so this is non-constructive. So for sure, there are two irrational numbers that when you say x to the y, you get a rational. But I don't know what those two numbers are. I know there's some of these, but I don't know which. Does that make sense? All right. So I want to talk briefly about counterexamples before we leave today. So counterexamples. Everything we've seen so far proves a statement is true. What would we do if we wanted to prove a statement false? So to clarify, if I wanted to show for all x, px is false, what should I do? Find an x. Yeah, find an x that doesn't work. Okay? So this x here is called a counterexample. It's an object in the universe of discourse that shows that the property doesn't hold for everything. There's at least one exception. So as an example, if I wanted to disprove every positive integer is the sum of the squares of three integers. Well, to do that, all you have to do is come up with a counterexample, and the counterexample to this is 7. Right? The squares smaller than 7 are 0, 1, and 4. Those are the only squares smaller than 7. And if you exhaustively try all combinations of these three squares, you'll see that none of them work. Does that make sense to everyone? So it can't be 4, 4, and 4 because that's 12. It can't be 4, 1, and 1 because that's 6. It can't be 4, 1, and 0 because that's 5, and so on. So after trying all combinations, you'll find that none work. Therefore, 7 is a counterexample. I'm not going to go through and do the full exhaustive search, but you guys can do that as an exercise. So when you do a proof by counterexample, there are two components to it, just like there was in an existence proof. You need to give your counterexample, and then you need to show that it's a counterexample. You need to give some reason. So I couldn't just say 7. I need to say 7 because these are the squares smaller than 7, and when I add them together in this order, I get this. When I add them in this order, I get this, and so on. The hint that you might have to do a counterexample is if the question says prove or disprove. In that case, this claim could be either true or false. It's up to you to decide. If you think that it's false, give a counterexample. If you think that it's true, give a proof. And you'll see an example of that next week. Any questions before we go? Yeah? No, because those aren't squares. So the only squares smaller than 7 are 0, 1, and 4. I'll maybe take that offline. That's it for today, guys. Remember to go to your tutorials.